We present our work in this video. Efficient video object segmentation via modulated cross-attention memory. Given a mask of objects, our method segments long videos in real time with high FPS and less GPU memory demands. Our method runs at 37 FPS on V100 GPU and 52 FPS on A100 GPU. The goal of visual object segmentation methods is to accurately identify and track the specified targets throughout the entire video given the first frame. Owing to the success of transformers in several vision domains, the recent methods formulate the transformer architecture into VUS framework for frame embeddings. Usually, the main building block of these methods consists of long-term attention to propagate the target information from the memory frames and short-term attention to match the current frames with the embeddings of the nearby frames. In this work, we propose a novel and efficient approach for long video segmentation. Our transformer-based approach introduces an optimized and dynamic long-term modulated cross-attention memory requiring memory expansion. We establish meaningful and concise connections between memory frames at various time steps to effectively propagate the target information from past frames. Unlike the current transformer-based approach, the proposed MCA memory maintains consistent speed and GPU memory requirements regardless of the video length. We compare our proposed method with the recent transformer-based methods in terms of FPS and mean frames per video along with GPU memory consumption in gigabytes. Recent transformer-based approaches exhibit a substantial reduction in speed and memory explosion for long videos. In contrast, our method maintains consistent speed without GPU memory issues and no significant performance degradation in both short and long videos. FPS is measured using V100 GPU. On the right, we can see our results on long videos from LVS and LTV datasets showcasing robust performance with more than 120 seconds for LVUS and more than 3,500 frames for LTV dataset. The design of the long-term memory for the existing transformer-based approaches is not well suitable for long video. They keep expanding the long-term memory every few frames to add new information regarding the target. This leads to slow processing speed and ever-expanding memory with increased GPU memory demands, especially when dealing with long-term videos with thousands of frames. In this work, we propose an optimized and dynamic design for the long memory. The proposed modulated cross-attention memory consists of 2 frames regardless the video length. It contains the reference frame and a single dynamic frame. The goal of the dynamic frame is to encode the temporal smoothness without requiring memory expansion. It effectively encodes both local and global features at various levels of granularity. Our method has real-time speed and consistent GPU memory for long videos. The video frames are passed to the lightweight encoder to extract the frame features, followed by the proposed ELSDT block to handle the long-term memory efficiently, followed by the decoder to generate the final masks. The ELSDT mainly consists of short-term propagation to encode spatial information of the target from the previous frame and long-term propagation to propagate the target information from all past frames. Here, the long-term propagation is based on the proposed MCA memory. In the MCA memory, the new memory information is projected to queries and the memory context is projected to keys and values. We apply hierarchical contextualization using depthwise convolution to generate the local context and multiply it by learnable gates. The queries of the new memory is multiplied by the keys of the memory context to generate global attention maps. After that, the aggregated context is projected and multiplied by the attention maps to generate the output. For more details, please check our paper. We evaluate our method and the most common VS methods on the widely used short and long video benchmarks. In Table 1, we show the number of videos, mean frames per video, number of objects, and the number of annotated frames for each dataset. We present a quantitative comparison with state-of-the-art models in zero-shot settings on the validation set of LVS. The FPS of all methods is measured using V100 GPU. Our method performs favorably in terms of accuracy with superior speed against existing transformers-based methods and achieves an optimal trade-off with different backbones between the accuracy and the FPS. In addition to LVS, we compare our method with the current state-of-the-art models on LTV dataset. Among existing works, Eximium runs at 23.7 FPS with accuracy of 89.8%. Our method with SwinB achieves 90.3% while running at 22 FPS. To show that our method also performs well on short videos, we further report results on Davis dataset. Our method achieves faster inference by nearly 10 FPS compared to the baseline DAOTL with only a negligible 0.1 drop in accuracy. Similarly, our ResNet 50 and SwinB variants achieves 85.6% and 86.4% respectively. This shows the generalization capability of our method for both short and long-term video datasets at a significantly higher FPS and less GPU memory consumption, especially for long videos. The ablation studies are presented in our paper. We show a challenging video case from LVOS validation set with more than 120 seconds. Given a mask of two objects, our method shows impressive performance for the long video. It accurately segments both targets despite the challenging scenarios, such as the closing and opening of the umbrella at many frames and the severe occlusion and swapping between both girls. Notably, our approach maintains real-time FPS. The processing of this video is at 37 FPS, which showcase its efficiency in handling complex scenarios for long videos while ensuring accurate segmentation for multi-objects. In this video, the target for segmentation is the smallest zebra. Despite the similarity and occlusion between the target and other zebras at several frames, our method accurately segments it based on its mask without confusion. Additionally, there are instances where the target disappears behind a tree in certain frames, and our method successfully segments it again once it reappears without drifting. To summarize, the key advantages of our proposed method are real-time FPS regardless the video length, significantly less GPU memory consumption compared to the current transformer-based methods, state-of-the-art performance on LVOS dataset. The main technique contributions are efficient and optimized modulated cross-attention memory for long videos, effective memory design to propagate the information of the target from the past frames, new fusion operator that combines the merits of cross-attention and focal modulation techniques to encode local and global information at various levels of granularity.